I'm going to sort of be covering what I see as like the current state of interpretability, like what people are trying to do, what the best methods for trying to do those things are, and then how people are trying to scale up our efforts and what I think might be some good adjustments in our current efforts on that end. To start, I'd say that interpretability can be roughly understood as being able to provide us three things when it comes to models. It could give us the ability to predict models, what's going on in their heads, predicting their thoughts. We can control models. Can we do something like little neurosurgeon interventions to control what they're doing? And then it also helps us understand models. Like, what are the processes and algorithms they use to solve the interesting tasks that we know they're able to do today? I'll start by just going through these three sections and saying what I think the sort of state of the art is. I actually think that prediction hasn't changed too much, maybe in the last 10 years. I think we've deepened our understanding, but I still think if you want to sort of predict something out of a model and get a correlational measure of a concept, you would use a probe. So all a probe is a supervised classifier model that you train to predict out concepts from internal neural representations. What this looks like is you might have part of speech, or you might have positive sentiment, and you try to train out, is this piece of text expressing positive sentiment, or does this particular word belong to this part of speech? And this is a supervised method of getting a correlational measure of model representations. Then when we move on next, we can see that probes are actually really the way to understand them is that as you have an arbitrarily powerful and complex probe, you just measure the mutual information between an internal representation and then some concept that you're trying to understand. So you might just measure the mutual information between a vector representation created processing a restaurant review and then the concept of that restaurant review expressing a positive sentiment about the restaurant. Typically, probes are trained on the internal representations of model, and then we just use labeled data to get them to predict out concepts, and they tell us something about where information lives. Typically might train a probe to predict out the thoughts of the model, what concepts are active in its head. We might also train a probe to predict out a future model behavior, and that could have particular implications in more safety-oriented settings. But really, I don't think too much has changed since in maybe like 2016, 2017, when we started using probes to try to understand neural networks. And this was before we even had large language models. And I think that's about where we are. So control is kind of a weird topic for interpretability, because really, I think all of machine learning is about controlling these objects in some way, right? I think fine-tuning, I think prompt engineering are just ways we interact with large language model technology and then try to get it to do particular things. I would say fine-tuning is a default method for control. It's a very powerful method that we should always think of as the obvious sort of baseline method when we're trying to adjust a model or align a model in some way. We also have parameter efficient fine-tuning methods. This means you don't have to update all the weights of the entire model. Rather, you choose some small slice or proportion of the weights, and then you update that slice to be more useful for a downstream task. And this is a pretty expensive method of control, right? If you want to fine-tune something, you need to articulate your desired behavior in some data set, and then use this data set as a source of supervision for updating the parameters of the model and creating a new object. After fine-tuning, we can talk about prompt engineering. Prompt engineering is a very intuitive way of interacting with and controlling a model, and should also be considered a very strong baseline for how we want to align our models. All you do with prompt engineering is you just ask the model to do something. If you want a model to talk positively about a topic, just ask the model to do that. If you want the model to speak in French, say, please speak in French. You can do this intuitively, just typing it out yourself. There's also automatic methods for prompt engineering and coming up with some sort of sequence of text that's going to put the model in a state where it's amenable to do what you want. Now I'll move on to what is now kind of like an exciting area of research, but also one I don't view as like fully justified yet, which is steering. So steering is a method of controlling a model via interventions on internal representations of the model. So if you want the model to express a positive sentiment about weddings, you would inject in some little signal that says like positive direction weddings. And this is an example of a steering task that people have done. But I think the question is like, when is this actually the best way for interacting with a model? Here's a basic method for steering that I just described that could solve the task I just described of like having positive sentiment about weddings. So you have a bunch of text that express positive sentiment about weddings and a bunch of text that express negative sentiment about weddings. Then you take some vector representation created by the model on all of those different inputs. You take the average positive wedding vector, the average negative wedding vector, and then the direction between those two means, those two average representations. This direction is some sort of slider that you can intervene on the model and increase a signal or decrease a signal that is saying, like, how do I feel about weddings, positive or negative? This is the figure from the paper that does exactly this weddings thing. And this is just a difference in means steering vector. And it's a very intuitive thing. You just define two polarities with some data, and then you take the average representations, you take the difference between them, and now that's a direction you can inject into your transformer model to try to get it to act in a certain way. Other steering methods might use sparse autoencoder features, which is something I'll loop back to later, but they also might just do dimensionality reduction, say PCA or SVD, on some vector representation across many different inputs. And that would give you also some directions you could try steering the model in, meaning increasing the activation along a particular direction in vector space. Concept erasure is just another method people talk about all the time. So erasing some concept, you can think of this as steering. It's often done via sort of ablating vector directions. So you set them to 0. And this is just another way that people interact with the model, do something to its insides to try to elicit some downstream behavior. Also, there are increasingly more methods that sort of exist in this intersection of steering and fine-tuning. So localized fine-tuning is a paper I saw at NeurIPS that is sort of, first it figures out what are some small number of attention heads that are relevant for a transformer performing a particular task, and then it learns steering vectors specifically for those attention heads. What I really think all of this steering work needs to do is we need to establish some baseline evaluations and benchmarks and data sets for controlling models, and we need to compare steering methods against fine-tuning and against prompting and figure out whether they ever have competitive advantages. And I think a lot of the most basic ways you would define these steering tasks, like the be happy about weddings, be sad about weddings example and the figure I showed on a previous slide, that is going to be pretty simple to do from fine-tuning and from a prompting perspective. And if you just ask the model to be positive about weddings or negative about weddings, the model is like perfectly happy to do that. And so if we're going to justify doing interesting, cool interventions on the inside of models to control what they're doing, we need to articulate the domains in which that is going to be a useful thing to do, and that it'll be actually state of the art in some sort of way compared to prompting and fine-tuning. Something I want to finally mention is a work that I was a part of, which is representation fine-tuning. And you can think of this as some sort of like middle ground between parameter efficient fine-tuning with like LoRa's and doing some intervention or update to the model. And all representation fine-tuning is basically attaching at a small number of locations just little low rank linear MLP transformations, basically. You might have some sequence of text and some layers of a transformer model. And then all this method will do is say, at these given tokens and at these given layers, attach a little module that will do a little update of the representation. It'll read out a little bit of information and then write in a little bit of information. And so these are very, very parameter efficient sort of models. They're much smaller than LoRa by like a factor of like 1,000 to get them to work, but you can still radically control and update the base model using these representation fine-tuning little updates at a handful of locations. I'm excited to see work in this area, and I'm excited to see us exploring sort of different ways of interacting with and nudging the model to do certain things. But I think I'm most excited about seeing benchmarks and evaluations that's going to help us figure out the space better and order our methods by usefulness along certain dimensions. Now I've sort of covered the prediction, which is like just predicting out correlations from internals of models, and then control, which is trying to get models to do something and how that might relate to interacting with model internals. And now I'll move on to understanding, which is my personal favorite part of interpretability and really the central thrust of my entire time as a PhD student. I'd like to take a couple steps back and zoom out when I first talk about understanding black box AI systems today. So first, I just want to think about computational explanation as an idea. So as people trying to understand the world and as scientists, we approach certain dynamical systems with a mindset that they implement algorithms and that this is the best way of scientifically understanding the system. So a human doing mental math or doing lots of different things. This is sort of the foundation of modern cognitive science, a functionalist theory of mind saying that the brain is something akin to a piece of hardware that is running software or algorithms through it. Deep learning model, I think people also have these intuitions that they're running algorithms when they do, especially sort of reasoning type tasks. And then also a physical computer. This is like the most canonical example of algorithmic implementation in our world. Python programs describe some abstract flow of information that is indeed realized up to some fudge points inside our physical computer. This is the zoomed out view I like to take. So like we're really just thinking about algorithms, systems, and implementation. Like what does it mean for a system to implement some sort of algorithm? And so something I guess I kind of stumbled upon or came to realize is that we didn't have a super mathematized or precise way of talking about this up until this point. There's some sort of like literature and philosophy about what computational implementation is, but it's actually an open question still to this day in some ways about what precisely defines the relationship of implementation. But the approach that I've taken in my work, and I think it's a very broad and general approach, is to understand everything via causality. What this means is you can represent both a dynamical system, like a deep learning model, and an algorithm as a causal model. What is a causal model? Causal model is just something with discrete graphical structure. So it's a bunch of circles, a bunch of arrows between those circles, and then functions that tell you, how do I know the value of this circle based on the circles that are pointing to it? So it's just discrete graphical structure with functions telling you how information flows across it. So it's a very generic mathematical formalism, and it's not surprising you can write down neural networks as causal models. All the pictures we see of neural networks are just circles with arrows, and we know those arrows are representative of linear algebra functions. Algorithms, some people might not intuitively immediately think of them as causal models, but you can actually really, at some very high level of fidelity, like represent things like the bubble sort algorithm as a causal model. When you sort of accept that these are two systems that can be perfectly inscribed as causal models, the natural thing is to then encode them and understand implementation, the relationship between these two systems, as a matter of causal abstraction. And that is the sort of like really the keyword central thrust of my research program is basically that causal abstraction, which is just understanding when does a tiny process realize a larger process, is the right way of approaching computational explanations. When we want to understand, does some tiny process, like an algorithm, is it truly realized inside this larger, more complicated black box system? What we need to do is interventions on the black box system and our hypothesized algorithm and show there's a correspondence between the effects of the interventions at both levels of abstraction. Just staying zoomed out here, the theory of causal abstraction was developed in a couple of domains. This involves analyzing brain data, analyzing neural networks, artificial ones, and also analyzing the weather. So these are all very complicated, dense black box systems, but the theory that has been building up around them is understanding how do micro variables get faithfully aggregated or simplified into macro variables to help us understand and eventually downstream control, predict, and use these systems. I'll just pause here to really make my pitch, which is like, I just think it's the most exciting time in history, basically, for people who want to analyze complicated black box systems. The weather and brains, they exist in the world, and people are struggling to try to understand them, but we have such poor experimental access to these objects. The types of tools that we have available to us in the sort of like artificial deep learning domain is just insanely idealized neuroscientist. We can freeze, we can run back, we can lesion, we can stimulate, we can patch in the thoughts from one run to the thoughts on another run, sorts of things that people just like would fantasize about in a neuroscience field. And so that's really the reason I think that like in the last like 5-10 years and like moving forward, we're just making a lot of progress on these sorts of cutting edge, interesting theoretical and empirical problems. And we're doing it from this sort of like subfield of AI interpretability. So that's my call to action for everyone. So do the research that I like, basically. with a lot of other people, have put out this very long theory paper that sort of articulates the relevant mathematical notions for causal abstraction and just in a very sort of like just causality math way. And then the second half of the paper goes through a wide range of mechanistic interpretability methods, so methods for analyzing model internals, and shows that they can be understood in the framework of causal abstraction in a very mathematically precise way. So these include path patching, causal mediation analysis, causal scrubbing, causal tracing, circuit analysis, concept erasure, sparse autoencoders, differential binary masking, distributed alignment search. And see, these are all just like, I'm just zooming through like all of these, but these are just like 6 or 7 different methods developed in the last 5 or 6 years that are all in very nuanced ways, like very similar and slightly different from each other. And so I think this sort of like unifying framework gives us an ability to take stock and see which methods belong to sort of which families and whatnot. So that's my very zoomed out sort of like view of like how I view the field, like where we should be going. But now I'm going to zoom in a lot and just walk through a very tiny experiment that is what we do when we're trying to do a causal abstraction analysis and understand a system. The recipe that we've been talking about is that we state some hypothesis about the structure of a black box system. We choose some alignment. So that means like we find the high level variables and we say, where are they actually realized in the black box system? So align them to components of the black box system. And then we do these interventions we call interchange interventions because they simulate a very specific counterfactual scenario. Here's the example. Say we have some neural network and all it does is it's trained to add together x plus y plus z to give you some output sum. And then you have a hypothesis about how it does this. You say, I think it adds together x plus y first and stores this in a variable s1. And I think it stores z in the variable w. And that's here on this left side, this green graph. This is the high level structure we're saying we think exists in the model. The dotted arrows are the alignment. This is saying like, where do we think these high level variables are being realized inside the low level black box system? Now I'm going to show you an intervention experiment that goes towards trying to verify that claim. Say we have the input 1, 2, 3, and we have the input 4, 5, 6. This is what would happen at our high level when we run these models. So 1 plus 2 is 3, 3 plus 3 is 6, 4 plus 5 is 9, 9 plus 6 is 15. But then say we do an intervention where we place the value 3 and set it to be what it would have been for the separate input. It should be a 9. Now what that would do is increase the total sum by 6, from 6 to 12. So this is just all a statement about our high-level hypothesis and has nothing to do with the black box system we're analyzing yet. But the question is, if we think that the sum lives in this far left vector representation of the neural network, then we should be able to do the same intervention and have the same outcome. So we take 1, 2, 3, we take 4, 5, 6, we run them both through the model, then we patch in this representation that we think contains the sum. And then if the output goes from 6 to 12, then that is a piece of evidence in favor of our hypothesis. Doing the intervention at the high level, the outcome of that was the same as doing the intervention at the low level for under the given alignment we have, this dotted line between the two models. And so this is just one example of an intervention, but aggregating these interventions, so say, take any 2 pair of examples, do this intervention at the high level and do it at on the black box system as well, then we can quantify the correspondence on average between our hypothesized structure and the actual underlying low-level black box system. And so this is the sort of workhorse of all of the research in the sort of understanding and localizing concept flow inside networks, is doing these patching experiments, because rather than something like a lesion where we kind of destroy information, this is a very precise manipulation of the representation. It's going from 3 to 6, so we know exactly what the output should be if we are right about the structure. So that's the sort of covering causal abstraction analysis. Like that's the intervention technique that we do when we're actually trying to verify these claims. And I'll now quickly talk about a couple other things, which is instead of if we're not in a verifying mode anymore, and instead we want to train the black box system to have a particular structure, that's a very straightforward thing to do in this framework. And you can use some high-level structure as a source of supervision for training a low-level system to localize concepts in particular places. That's called interchange intervention training. And then The really exciting tool, I think, is distributed alignment search, which is where we freeze the black box model. But what we instead do is we use gradient descent to learn the location a concept is stored. The way we do this is that we, instead of trying to localize a concept to some vector representation, we want a linear subspace of a vector representation. So some set of orthogonal vectors that span some chunk of this subspace. And then what we want to do is learn these orthogonal vectors, because these will define where we perform an intervention. And we use the signal of what we want our intervention to do to learn where we're doing the intervention via these orthogonal vectors. So this is like a much more complicated idea, but I think this is really our most exciting tool, is that we can use gradient descent to localize a concept inside vector space. And that high-level sentence is the core takeaway. The next core takeaway after that high-level sentence would be that the way we do this is by learning orthogonal vectors. And that is really just some sort of spanning set. So some sort of just linear subspace inside high-dimensional vector space. That is basically what I would say. This is basically what I would say is like the state-of-the-art supervised method for localizing concepts inside of a model. And it's a pretty exciting tool that's only really starting to be used in the last like year, but pretty much every project I've been involved with where we're using it, it's been pretty useful, pretty exciting, and gives you the ability to actually apply supervised machine learning to understanding black box systems, which I think is a very powerful connection to make, because a lot of the work beforehand was doing hand-picked sort of analysis where you would say like, I'm going to search through a bunch of locations and just do a bunch of experiments and try to figure out where I think things are. But now this is a process that can be largely automated by gradient descent, which is just incredibly huge, I think, for a field. So I'll spend my last maybe like 2 or 3 minutes just talking about how people are scaling up sparse autoencoders, or how people are scaling up interpretability, and they're using sparse autoencoders to do so, and some core takeaways I have from thinking about how we should approach scaling things. So I'll quickly go through what sparse autoencoders are. So sparse autoencoders are just autoencoders, so they're trained to reconstruct representations of model internals. So you have a language model, you have a huge amount of text, and then you just train an autoencoder to project a vector up into high dimensional space, and then into a sparse high dimensional space, and then project that sparse feature vector back down into the dense low dimensional space. And the way they do this is with a linear encoder and a ReLU to get up into high dimensional feature space, and another linear decoder to get back down into the original vector space. And they just train this linear, ReLU, and then linear, this model, on a large base of text. And then they get these featurized vectors from them, and they automatically label the features in this new high dimensional space using these autointerpretability pipelines, where they basically like generate a bunch of text that makes some feature fire, and then they try to reverse engineer what does that feature mean based on the text that made it fire. So these are like unsupervised objects. These features, they don't know exactly what they mean. They've just trained an autoencoder to take a dense representation, project it into high space, and project back down. So they can have unexpected concepts in this high-level feature space that you then have to kind of discover by figuring out and experimenting around. And people tout this as like a benefit of SAEs. I really think if you want a feature for a specific concept, so if you want to be able to predict something or steer for something or understand where something is localized, you really would never use a sparse autoencoder to do this, because this is an unsupervised method. And if you can articulate what you want out of a probe or a steering vector or a localized component, if you can articulate that in the form of data, then you can use that data to as a source of supervision to learn the model internals that do what you want. So basically, like, my contention would be that across these 3 domains of prediction, control, and understanding, if you have a specific concept you're looking for and trying to understand in the model, you should just generate some data that has to do with that concept. What should happen when it's steered for? What should happen when it's not steered for? What should happen when it's localized or intervened on? And then use that data to help learn a steering vector or learn the component where that concept is stored or train a probe for predicting out that concept. And then a final point I'll make is I think the exact same data that you would need in order to figure out what sparse autoencoder features actually are and verify if they're useful in the ways you want them to be if that's the exact same data you would need to do the supervised training. And so I'll end my talk on these 4 points. So the first thing I want to see out of scaling interpretability is I want us to use counterfactual data when we're doing our scaling efforts. The sparse autoencoders are trained on an observational distribution of model internals. If you want a mechanistic understanding of an object, you should not just observe and then try to reconstruct your observations. You should do interventions and then get the rich data that comes from doing interventions and use that data as a signal to train whatever the object is you're trying to scale up for understanding. This is an a priori, like very obvious thing to me coming from the causality literature. And I think the causality literature is just undervalued by interpretability right now. And that some very basic observations in this area would have massively adjusted, I think, where all of the industry labs are going, because all the industry labs are going all in on sparse autoencoders right now. And I think there's a lot of room for variety. I also want us to pre-register our criterions for success. If we want to scale up something and make it release it out into the world, I think we should say beforehand, what would it look like to have a successful version of that object? I think in sparse autoencoders case, we kind of did the opposite, where we scaled up a lot of stuff, and now we're reverse engineering what could this be useful for. I just think this is like a good way for responsible science to proceed. I think we publicly say like, here's a data set that articulates some problem or some use case that we want, and now we need things that help us do this. Dynamically constructing features based on context. The whole SAEs just assume that some vector can be understood in a model without looking at what's happening around it. That could just be wrong. There might be no way of featureizing a vector to figure out what concepts are in it without looking at other vectors in the model. I think that's entirely possible and kind of ignored by the architecture. And finally, I think we should remain open-minded about nonlinear features. I don't think everything has to be linear in a highly nonlinear model. We can get a lot of purchase out of the assumption that linear features are there and useful, but that doesn't mean we should sort of be ideologically committed to that. I have a benchmark paper where we're working on benchmarking for localizing concepts and models that was at some ACL conference last year. We are working on scaling up a sort of supervised version of feature learning in this paper called HyperDAS that'll probably be released this week. And then for nonlinear representations, food for thought, we had this black box NLP paper that is about understanding a different type of representation in recurrent neural networks that isn't linear, but rather uses this weird packing operation with order of magnitude. Those are just food for thought going in directions that I think we should be going. I think I can just end there.